Okay, so last time we came up with the design equation for each of the three reactors that we'll be using for most of the course. This time let's try to optimize the total volume we need for a reaction, and we're going to do that with the Levenspiel plot. The way we do this is first by taking those design equations that we had last time and putting them in terms of conversion. So this is what we came up with last time for the batch reactor, the CSTR, and the PFR, and these are the design equations that we came up with. And remember, a design equation just relates the volume of the reactor with the reaction rate and the moles within the system. So here you see volume, here you see reaction rate moles, here you see volume, here you see reaction rate moles, and here you see volume, and here you see reaction rate moles. In a batch system, we generally look at N sub A, which is just the moles, and in a flow system, we look at the flows, the moles per time. So in the batch system, you'll see this N, and in the flow systems, you'll see this F. So let's talk a little bit about what conversion means and why we care about conversion. Alright, so let's first define conversion. So let's say you have a species A. Let's call X sub A the conversion of species A. We're going to say the conversion needs to be between 0 and 1. It cannot be greater than 1, it can't be less than 0. Now, if our conversion is 0, what that means is that nothing has happened in the reaction, so we haven't lost or gained any A. But if the conversion is 1, and what that means is that the reaction has gone to completion. So if A is a reactant, we've lost all of the A in our system. It has been completely consumed. And this is true for irreversible reactions. Notice we must say this is true for irreversible reactions. Perhaps you remember from general chemistry what an irreversible reaction is. It's a reaction that will generally go all the way to completion because the equilibrium constant is so large. So all of A has a chance of being consumed. If you have a reversible reaction, then what happens is that the upper bound over here is going to be some equilibrium conversion. It's not going to be 1. It's going to be some point less than 1. But we're generally not going to worry about that in the context of Levenspiel plots. So again, conversion cannot exceed 1, and it cannot be less than 0. Okay, so mathematically, how do we define the conversion so that actually fits these rules? Well, we're going to say it's the initial moles in the system minus the final moles in the system all over the initial moles in the system. Or consequently, for flow systems, as we were talking about the difference between that N and that F up there, if you have a CSTR or a PFR, it's going to be found like this. The initial moles flowing into the system minus the moles flowing out of the system, all divided by the initial moles flowing into the system. Alright, so why does this make sense with the rules that we have up above? So when your final moles are equal to the initial moles, what that means is that at the beginning of the reaction and at the end of the reaction, you have the same amount of A. So if N sub A equals N A naught, then you're simply going to get 0, which means the reaction did not occur. Likewise, if everything is consumed, what that means is that at the end of the reaction, N sub A is 0. There's no moles of A left. So N sub A minus 0, all divided by N sub A, naught is going to simply get you 1, which means the reaction went to completion. Now this could be the same done with this definition up here, and that would be for flow systems. So if you had F sub A naught minus F sub A naught over F sub A naught, that would be the same conversion definition for a flow system. Okay, so typically you won't see the conversion expressed like this as the quotient. Typically when you use it, you'll see it used like this. Let me put flow over here. So it's just going to be rearranged with this N sub A naught is multiplied over here, and then everything's distributed so that N sub A equals N sub A naught minus N sub A naught times the conversion. Or similarly, if you just use the distributive property, you can just pull that N sub A naught out and write it like this. And the reason why we care is that typically you're going to be using, or you're going to be getting the conversion when you have N sub A or F sub A. Maybe that doesn't make so much sense now, but when we actually work with the design equations, you'll see what I'm talking about. So let's just jump right in and take a look at that. So the objective right now is take each of the design equations that we have for each of the three reactors that we've been dealing with and put them in terms of conversion. So let's start with the batch reactor. This was the differential form of the design equation that we came up with on the last video. If you want to see where that comes from, just simply watch the last video. And the next thing we're going to do is we're going to take that definition of conversion, rearranged of course. Remember, like I was saying, this was the original definition. We simply did a bit of algebra and put it in the form that looks like this. You'll see why I did that in a sec. So that's our definition of conversion. Now the design equation over here, if we want to put it in, we need to take the derivative of this equation with respect to time. So that's exactly what we're going to do. If we take the time derivative of each side of the equation, what you'll see is this. I'm going to go through all the gruesome details just so there's no misconceptions. You're able to take the derivative of this and the derivative of this, because remember, the derivative operator is linear, which means you could distribute it over these two when you're multiplying it out. And since n sub a naught, the initial moles in the system, is a constant, that's simply going to be 0. Similarly, since this is going to be constant, you could pull it out of the derivative operator, and you're going to get the conversion as a function of time. The conversion as a function of time is not going to be constant. As the reaction goes on longer, and as you wait more time, it's going to go further and further to completion. So if we take that original design equation and we sub in this line here where we took the derivative of the conversion definition, what you're going to get is, first of all, we just plug this in here, and then in general you'll see it rearranged in this form. So this is the final design equation for the batch reactor in terms of conversion. Why do we have this? Well, a positive rate is for generation and a negative rate is for consumption. Generally, when we're talking about conversion, we're talking about A as a reactant. So as A is being consumed or converted to a product. So negative rate is just saying, okay, this is the consumption of species A. Okay, we have the batch reactor design equation. Let's look at the CSTR. So this was our CSTR, and this was the design equation that we came up with last time for the CSTR. Once again, we're simply going to take that definition of conversion. This time, notice that there is F's instead of N. The reason for that, again, is because the F is for a flow system and the N is for a batch system. And you can convert between the two. The only difference is time. So N sub A is in moles, F sub A is in moles per unit time. Okay, so that in mind, we're simply going to, since we have the F sub A up here, we don't have to take the derivative, we can just plug it in directly. What you'll see is this. So if you take the F sub A naughts, you'll see that they will cancel out. And this minus sign over here is going to make this positive when we compute this. So the design equation in terms of conversion is actually really easy to get, is simply going to be this. The one caveat is that we need to look at the reaction rate that happens at the exit. So as this stirs all the way around, when we're talking about conversion, we're talking about the particles that are leaving at this end. And we're talking about, okay, how far converted are they going to be? Even though it's well mixed, even though the reaction rate is the same at all parts of this reactor, what we're concerned about is conversion at this point. So the conversion at this point might not be the same as the conversion at this point. Again, that's because as the particle stays longer within the CSTR, as the longer amount of time to react. Typically when you're expanding the volume of your CSTR, you're elongating the mean residence time of the molecules in there. Again, what that means is mean residence time is the amount of time it takes for a particle here to get to the outlet. So if the reactor is larger, the particle is going to spend longer time in the reactor before they get to the outlet. And that gives them more time to react. So the volume here is really just giving you more time for the particles to react within the reactor. Okay. Lastly, let's take a look at the plug flow reactor. This was our plug flow reactor. And this was the design equation we came up with last time for the plug flow reactor. Again, we're going to use the definition of conversion. And this time, since we have a derivative in there, we're going to need to take the derivative, much like we had to do with the batch reactor. So if we take the derivative of this with respect to V, It's going to be the same thing as last time. This is constant, so it's going to cancel out. Over here, we're going to be able to pull that f sub a naught out, and the conversion this time is going to vary with the volume of the PFR that you have. And the final design equation, if we combine this up here with this, is simply going to look like this. And again, we're going to move that negative sign over. Instead of having it on the left, we're going to have it on the right, because again, this rate is for A being converted, or A being consumed as a reactant in generating products. Okay, let's take a step back and look at how our design equations have transformed. So we went from these design equations in the differential form to these new design equations in the form of conversion. The advantage here is that, instead of saying, okay, I have this many moles in the system, what does my volume have to be? You can instead say, this is how much moles I'm feeding to the system originally, right? N sub A naught, F sub A naught, F sub A naught. So say I'm feeding like 10 moles to the system, and I want a conversion of, say, 90%, I know how big to make my reactor, rather than just saying, this is how many moles go in, this is how many moles go out. I have some data about the reaction rate, how big should the reactor be. It's more useful in terms of reactor sizing, because I could actually say, I want my reaction to go most of the way to completion, or not so much of the way to completion. Okay, so what if we have a more complicated reactor system? So take a look at this. Say we have CSTRs in what we're going to call series. What that means is that the outlet of one of these is connected to the inlet of the next one. So you have a first CSTR, a second CSTR, and a third CSTR. How can we express the conversion of this last CSTR over here? Well, we pretty much do the exact same thing we have been doing. So we start once again with our design equation. Notice this time it does not say F sub A0 or FA. We're saying this is the outlet stream of the second CSTR, and this is the outlet stream of the third CSTR, and this is the volume of the third CSTR. Then the next thing we're going to have to say is that, okay, we want the conversion for the overall process. Remember, back to our definition of what conversion was up here. We want the initial moles in the system minus the final moles in the system. Well, the initial moles in the system was over here entering the first CSTR, CSTR1. So that's F sub A naught, and the moles leaving the entire system is going to be F sub A3. So that's how we've defined our conversion to deal with multiple reactors. Once again, using the definition of conversion, rearranging that, we're going to get this relation here. And at this point, we could then say, for the conversion going into the reactor, at this point, that's simply going to be the conversion up to that point. So it's going to be the same relationship except for FA2, because it's going into the reactor, and this is conversion going out of the reactor. And again, we're going to use the conversion definition to relate the two of them together. Now, at this point, in doing all the algebra, it's going to look like sort of a mess. But we're going to sub both of these definitions back into this line here. What that tells us is that we could express the volume of the third reactor in terms of the conversion going out of this reactor and the conversion going into this reactor. Why do we care so much? Well, you're going to see momentarily. Okay, let's do the same exact thing for a PFR. So say we have some complicated reactor scheme going up into the PFR, and the PFR over here. Now we're concerned about looking at the conversion here. So again, we're going to start with the design equation for the PFR. And this time we want to get the volume of this PFR. This is going to be a bit simpler. We're simply going to say, okay, in integrating for the volume of this PFR, we're simply going to look at the inlet conversion here, the first X sub A, whatever was coming in here, and the outlet conversion over here, which is going to be over here. Remember, we need to include this right here in the integral because it's going to depend on conversion. Whereas this, over here, the initial moles in the system does not depend on the conversion. That's just whatever is going into the system. Okay, so now you're probably asking, why did we go through that complicated derivation there? And the reason we need that is for what we call a Levenspiel plot. So the point of a Levenspiel plot is it lets you minimize the total volume of the system with a given conversion in mind, with the design equation for the CSTR over here for some series. So this is the nth CSTR. You're going to have an inlet and outlet conversion, and over here for the PFR you're going to have an inlet and outlet conversion. Notice that's the exact same design equation we had before. If you consider this as the first reactor, you just simply set this to 0, then it's going to be the incoming moles times conversion over the rate. So this is just a more general form of the design equations that we came up with a few minutes ago. So the way the Levenspiel plot works is that on one axis you have f sub a naught over negative r, and on the other axis you have x. Notice the reason we have that is because, again, we're trying to minimize the total volume, right? Well, you see here we have f sub a naught over negative r, that's the y-axis, and here we have conversion, that's the x-axis, and over here we have f sub a naught and negative r, that's the y-axis, and over here we also have the integral of x sub a, which is the x-axis. So really the volume is going to be the area of this graph, and we'll see how that sort of changes. This line here is the relationship between these two things. We'll figure out how exactly they came up with that later. Right now you'll just have to say, okay, that's going to be given to us. So if I wanted to get conversion of, say, 0.2 using a CSTR, if we look at our CSTR design equation, our outgoing conversion is going to be 0.2 and our incoming conversion is going to be 0, so it's simply going to be the rectangle here, right? So if this goes to 0, it's going to be this, which is our y-axis, times this, which is our x-axis. So you're simply going to make a rectangle with the top right of the rectangle being this point, and that's going to be the volume that you get. Likewise, if you're working with a PFR and you're trying to get a conversion of 0.2, since it's the integral, it's going to just simply be the area under that curve. You're not going to have this extra space over here that comes with the CSTR. Similarly, if you had a, different profile here, with the line here describing the relationship between this and conversion was different, if it was downward sloping, then you see that the CSTR is going to be better. And the reason is because it's simply going to be the rectangle from this point on the line over to whatever conversion you had before, and for the PFR that's going to be the total area underneath the curve. Remember, you're trying to minimize volume, and on these plots volume is going to be the area, so you want the smallest possible volume you want for a conversion. So if I wanted a conversion of 0.6, the optimal reactor would be a CSTR. Over here, if I had a positive sloping profile over here, the best setup is going to be the PFR, because the CSTR gets this extra chunk over here. Okay. The reason we needed that general form is because sometimes the optimal setup that you have is going to involve more than one reactor. So if I have a reaction profile that looks like this, again, this is the relationship between this term over here and conversion. We don't worry about how we get it. And I wanted a conversion of 0.8, then the CSTR would get me something that looks like this. Should really go up to this point. Right? And the PFR would get me something that looks like this. Neither of those are very good. But what I can do is I could say, okay, I'm going to use one reactor that gets me up to, oh god, that was not what I wanted to do at all. I could use one reactor that gets me up to this point right here on the diagram, and then I can use a second reactor to get me from this point. What that does is you're saying I'm going to first use, say, a CSTR. So it's CSTR, I should do this black. CSTR in series with PFR, because because remember the CSTR is going to be a rectangle up to the point you're looking at, and a PFR is going to be this. And remember, it's the integral from the incoming conversion up to the outgoing conversion, which describes the area underneath this graph, as the PFR is the second reactor in your series. So what you should try is, I'm going to give you a problem. Try this one. I'm going to give you this reaction profile. I'm going to say, give me the optimal reactor setup for each of these conversions. So pause the video and give it a try yourself. Alright, I'm going to assume you paused the video. These are the optimal reactor setups. So for the first one, simply having a PFR up to that maximum there. The second one, since it's really low lying, you could actually just use a CSTR to get down there really quick and easy. For the third one, getting up to this point over here, you need to use first the CSTR to get you to this point, then the PFR. And the second one, you have options, or rather the fourth one, I guess. You could use a PFR up to this point and then a CSTR, but generally it's less expensive to have the smallest amount of reactors as possible. So it doesn't make sense to have 3 reactors, a CSTR, PFR, and a CSTR. It makes more sense to just have 2 reactors, so a CSTR and a PFR. I'll give you one more, just to get really good at doing these Levenspiel plots. So same thing, try to give me the optimal reactor setup for the smallest volume for each of these conversions. Pause the video and give it a shot. Okay, I'm going to assume you tried. So this is what the answer is. The first one, simply having a PFR, because remember your CSTR is going to be a rectangle up to here. You're going to get this extra dead space volume over here. Over here, to get this over here, you could use a PFR to get up to this point, and then a CSTR, which saves you on this area right over here. Over here at this top, you're forced to use a PFR again, because remember CSTR is going to get you this dead volume